Hi, welcome to the Signal Path. Today's episode is very special because it's the first Signal Path giveaway. But before we get to that, I wanted to talk to you about these NeoPixel LEDs which have become really popular recently. This particular product from Adafruit, it has 60 LEDs arranged in this circular pattern which you can program and then light them up individually and so on. So these little LEDs are one-wire addressable 24-bit color LEDs, so they're really powerful. You can create a whole bunch of interesting patterns, program them to have all unique 24-bit unique colors, and every internal protocol is already taken care of, so it does PWM internally. You don't have to worry about any of that. And because they use one-wire communication, they're essentially cascaded, so you can have many of them in a row and just program them all in a serial fashion and then turn them all on at the end when you're done. And this particular product has a vast Arduino library that is available that you can download with it, but I'm not going to use Arduino today. I have nothing against Arduino, of course. I think it has allowed a lot of beginners to get into electronics and create some really interesting embedded electronic projects. My only concern with Arduino is that it tends to isolate the beginners, the new users, from the small details that goes into making these things work, because everything is already taken care of it for you. So you're kind of using the software alone, and you may not get into the details of the electronics as much. So I recommend every new user who wants to start using Arduino to spend some time to really understand how these little development boards are made, how is the programming done, how are the crystal oscillators are connected, how is the power supply filtered, all these little details which you would otherwise ignore. When I started using microcontrollers, none of these things was available. So every time I wanted to play with one, I had to really wire one myself. I had to learn how to connect the crystal to my microcontroller, how to decouple the reset line, how to make sure that the IOs can drive whatever is connected to them. And all these little details are things that you don't have to worry about if you just pick up an Arduino and start using it. So what we're going to do is we're going to program this using C, using a PIC, basically straight up using a very simple circuit. And also we're going to measure the waveform and talk about some of the challenges that goes into programming these using C as opposed to assembly, which I believe the optimized libraries for Arduino internally actually do, because it's very hard to meet the timing requirements of these things with a low crystal oscillator microcontroller right off the bat. So let's talk about that, and don't forget at the very end there's going to be some giveaways. No, I'm not giving away this. What I'm giving away is much more useful than this. So we'll talk about it at the end of the video, and well, let's get started. So here's a closer look at this this little contraption here. So this is sold in 4 sections, and then you'd have to solder these in sections together. So the sections begin and end like so. You can see there's 1, 2, 3, and 4 of them. Let me zoom out the camera a little bit. Here we go. So you can see them better. So they come in individually separate pieces, and you have to solder them together. But it's really straightforward. And if you look closely here, there is a little spot here where, I hope this thing can focus. There's a little spot here where I have soldered these things together, and it's clearly labeled that there is a ground, a digital in and a digital out, and a 5-volt supply. So this is how these are cascaded between each section. So you want to share the grounds together, of course, and you want to connect the data into the data out, and that's how a chain is made. And then finally the 5 volts together. And once you reach a point, at the end, here's another section that I've connected, and once you reach a certain point where you want to actually connect to it, then you don't want to connect the in to the out anymore. So what you can see clearly here is I have soldered a 3-pin connector to it, and this 3-pin connector connects to the in on one side like so, and the D out is then connected to nothing. If I wanted to cascade another ring, then I would take the D out of this and then connect it to the D in of another ring. But this is all I wanted to connect together, so you get this nice big one. They also have smaller rings. But what is really actually happening? Let's take a closer look at one of these LEDs, these RGB LEDs here, and I actually happen to have a picture of it on my computer. So inside the LED, this is take a very high resolution magnified picture of it. So inside it, of course, there is an opening which is covered by a clear epoxy which protects the circuits. And here you can see the 3 pieces of semiconductor, this one, and this one, which are responsible for the red, green, and blue LEDs. Now, this is what's inside any LED. So if you pick up a red LED, you will only see one of these guys, where you can see there's a wire bond connection to the top surface, and the bottom surface of the PN junction is connected to this trace at the back, and that's how positive and negative is applied to the PN junction. Now remember that in order to get different colors from the LEDs, it has to do with the dopants used inside the semiconductor, and I've talked about that in a different video that I've made. The only thing that's interesting to note here is that you can see that each of these LEDs is sitting on top of its own little metal connection, and then they're sharing the connection in the middle here using these wire bonds. And then at the left here, you can see a piece of semiconductor IC, most likely a very old CMOS technology, maybe a 0.18 or a 0.35. I have to look more in detail, but it doesn't need to be very fancy because it's a reasonably low speed technology. Anyhow, it has to support 5 volts. So you can see a whole bunch of connection to it. So this probably there's a data in and a data out. One of these 2 pins is D in and D out, and the rest is VDDs and grounds. So this IC does 2 things. It receives serial data, and once the serial data is completely received, it decodes it. So based on the timing information, because it's only one wire, so there's no clock, so you're only giving it a single stream, so it's asynchronous. And that asynchronous data, depending on very strict timing requirements, is interpreted by the semiconductor. Then it decides what PWM it has to put on each of these individual LEDs, because it is expecting 24 bits of data, 8-bit per LED. And then it decides what PWM is appropriate to get the excuse me, to get the different brightness for each of the LEDs, in which then mix together and create all kind of colors. And at the same time, it buffers the data in and outputs it from data out, so that the next LED that's in the chain will receive the data. So how does it know when to light up, and how does each LED know when it's supposed to actually apply the PWM? So there's a little trick. If the data input remains low for longer than a certain amount of time, then the IC will interpret that as the end of sequence, and whatever is received, it will apply. Whatever is in its buffer, it will apply as a PWM. So for example, let's say there are only 2 LEDs in a row. You will put in the first 24-bit, it gets stored in this guy, and then once you push in the next 24-bit, the first 24-bit is pushed to the next LED. So it's essentially like a very long shift register that you're dealing with, except that there is no clock. It's an asynchronous shift register. So you're pushing 24-bit, gets stored in the first LED, you push in a second 24-bit, then the first 24-bit gets pushed to the second LED, and the last 24-bit then remains in this one. And then you hold the data line low for long enough, and then voila, both of the LEDs light up with the 24-bit data that's been stored in them. And then you can imagine this being extended to many, many more LEDs. It doesn't have to be 2, it could be 128 of them. So you have to keep pushing data in there, and once you've pushed enough data, then you hold the data line low, and then all of them will then light up. So this IC will then take care of all the PWM and all the other details. But it's interesting to take a close look inside it. You can take a magnifying glass or a cheap microscope and actually look at it yourself, and you can actually look at it when it's light up. So you can see, and don't look at it when it's fully bright, because you can hurt your eyes. Put it at a very low intensity, and then you can see individually each of these light up. It's pretty cool to look under the microscope. So what about the algorithm? How does this algorithm work? How does the communication work? Well, they happen to give us exactly what we need. I think it was page 27. Yes, there you go. Here it is. So they tell you how this one-wire communication works. Now, here's what I was talking about before. If you just use an Arduino, you would never come across this, because it's already all taken care of for you. But it's good to know how this thing works. So in order for the IC that's inside the LED to interpret a sequence of signals as a 0, you'd have to send it a short pulse that's high and a long pulse that's low. And if you want to tell it that the bit is a 1, you send it a long high and a short low. So unlike synchronous, where you send a clock with it, you don't need to, when you have clock, you don't need to send high and low, because at the rising edge of the clock, if the data is high, it will latch a 1, and if the data is low, it will latch a low. But since there is no clock here, you'd have to distinguish somehow between 1s and 0s in a one-wire communication protocol. And this is done in this case by the different width in the 1 and 0 with respect to each other. So if the IC sees a short 1 and a long low, it knows it's a 0. If it sees a long 1 and a short low, then it knows that it is a bit 1. And the exact timing of that is also given to you. It's written down here. It says that this period has to be 0.4 microsecond, and this period has to be 0.8 microsecond. And then it tells you that this one has to be 0.85 microsecond, and this one would have to be 0.45 microsecond. So they're essentially reciprocal of one another, meaning that this one is 0.4 microsecond, this one is 0.8, and this one is roughly 0.8, and this one is 0.4. So what we need to do is we need to write a code that does exactly this. I want to send a bit 0, then I send this guy. I want to send a bit 1, then I send this guy. Therefore, if I want to send 24 bits in a row, then I will have to send 24 times either this or that, depending on the configuration that I want. So for example, if I want to set the LED to be the maximum brightness on all the colors, so red, green, and blue to the maximum brightness, which will create the brightest white color you can see because they will mix together and create the color white, then you would have to send this code 24 times in a row. And if that's just for one LED, if I have 60 LEDs that I want to all turn on to maximum brightness and the white color, I would have to send this 24 times 60 and then hold the data line low for 50 microseconds, and then all of them will light up simultaneously. Well, this all sounds really nice and easy, but there are some complications to this, especially because this timing is actually quite small. 0.5 microsecond is beginning to be in the realm where a microcontroller with a low frequency crystal is going to have a hard time to keep up, because if you're using something like a C programming language, that code has to be compiled. And then once it's compiled, it's either compiled directly to machine language or it's compiled to assembly and then to machine language. Now, C code is a high-level language, which means that in order for you to use it, there is going to be some background functions and some background assembly code and machine language is going to run, which it might be invisible to you. So you may not actually meet this timing requirement so straightforward. This all sounds a little bit complicated at the moment, but I'll show you the code and we will actually measure the waveform and it will become clear why this can be an issue. But before we do that, let's talk about what platform we're going to use to run this code in. So here's my very basic evaluation board that I'm going to use. So again, I'm going to use something really bare bone, nothing fancy. This is you've seen this board before. I've used it in a couple of my other experiments. All it is that this is a PIC microcontroller that sits in here. All the pins are accessible. There's really nothing else in there except a switch, an LED, a USB port, because this particular PIC can have a USB connection, but of course you can't program this through the USB. You have to program it with the ICD, with the in-chip debugger interface. So you have this little voltage regulator here and some diode bridge in here to protect it, so even if you reverse the polarity, nothing would happen. And then I've connected the ICD programmer. This one I'm using is from CCS, which is a company that provides C compiler. So I have their programmer. This is their cheapest programmer that they have, and it's just connected with a cable to this. And I have a little on and off switch here, which I can control whether the ICD provides power to the evaluation board or not. But the reason I have this is because sometimes your evaluation board could require much more current than this guy can provide, because the whole current from this comes from the USB port, so it's limited to 500 milliamp anyway at most. So I can turn the current off, and that way it separates the VDD from this, and I can apply the VDD separately. If I want to apply the VDD separately, I just put in 12 volts through here, and the 12 volts goes through the voltage regulator, becomes 5 volts. This is a 7805 regulator, and then it powers this. And there is a crystal oscillator here. It's actually just a crystal, it's not an oscillator, and this is a 20 megahertz oscillator that I have on here. And this guy has a built-in PLL and a frequency multiplier, so even though I'm using a 20 megahertz clock, I can actually run the internal clock of this at 48 megahertz. So it's all nice and simple. And what we're going to do is we're going to connect this guy directly onto here. And I have a little cable here that I have made. It's very straightforward. The cable just plugs directly into here and is color coded like so. And there it is. So the red is VDD, white is the data in, and black is ground. So then I have these three guys at the end which I can plug directly into the evaluation board. And that's it. That's all you need to program this little guy. No need for an Arduino or anything. And this way we're going to write the code from scratch. And we're going to measure the waveform as it is expected, the waveform that the circuit actually expects. We're going to try and see if we can emulate that using C code. So let's talk about power consumption. Now normally you wouldn't worry about these things, but because we're connecting everything ourselves, we have to be very careful about how we handle this. So let's say that I want to power my LEDs. I want to power this entire thing directly from this board. Well, how would I do it? I already know right off the bat, without having to do any calculations, that it's not possible to power it from USB, because you can imagine all those LEDs will consume a lot of current. Well, how much current? If you look at the data sheet, at full brightness with red, green, and blue all turned on, each LED is going to consume 60 milliamps. So if you have 60 NeoPixels, you're going to need 3.6 amps of current available to it. So right off the bat, using the USB is out of the question, unless you never turn the brightness on very high. So forget about that. Well, we may be tempted to say, okay, well, we have a voltage regulator here. We have a 7805 here. Why don't we give this guy 12 volts like it's required? Put 12 volts in here. It's going to make it into 5 volts, and then we're going to power the whole thing from this. Well, we can do some quick calculation and see if that actually makes any sense. Well, if I'm putting 12 volts in, I'm getting 5 volts out. It means the voltage drop across the regulator is 7 volts. Now, let's make it simple, and let's just say that instead of 3.6 amps, we only need 3 amps. We're being very, very aggressive here. So if I need 3 amps and I'm dropping 7 volts across here, that means this regulator is going to burn 21 watts. Can this thing burn 21 watts? Well, what happens if it does? Well, a quick look at the data sheet will reveal that the thermal resistance of the regulator from junction to air is 65 degrees Celsius per watt, which means that if I burn about 20 watts in that regulator, the temperature rise over ambient is going to be huge. So it's completely unrealistic. It is completely unrealistic to expect this regulator to burn 21 watts. It's just impossible. Its temperature would immediately reach its thermal shutdown, and it will then immediately shut down within a very, very quick short amount of time, less than a second or so, maybe even. It will completely turn off. So powering it through the regulator with a 12 volt supply in is impossible. Even if I were to put in only 6, if I were to only give it 6 volts, and then get out 7 volts, which I cannot because this is not a low dropout regulator, but let's just say I could, that means that I would burn 3.6 watts in it. It would have 1 volt drop across it. It would burn 3.6 amps. It would be 3.6 watts. Even at 3.6 watts, this regulator without any heat sinks is going to be unusable because the temperature will still exceed the thermal shutdown of the regulator. So this immediately tells us that we shouldn't make that mistake, and we shouldn't try and power it through the regulator. We'll have to have a whole separate power supply for it, perhaps a switching power supply to power the regulator. So I'm going to use my Regal power supply to power the LEDs, and I'm going to just use the USB to power the microcontroller itself. But be very careful not to connect those two powers together. You can't connect the 5 volt power of the computer to the Regal power supply because they're not exactly the same, and there's going to be some current sinking and sourcing, so don't do that. What we're going to do is we're going to isolate the VDD of this guy and power it directly through the computer's 5 volt. We're going to share the ground of this and the power supply and the NeoPixels, and everything's going to work out nicely. So I'll connect it all up together, and let's look at the code next. So remember what it is that we want to accomplish in our code. We want to send a 0 by creating a short pulse and a long pulse, and we want to create a 1 by doing the opposite, a long 1 pulse and a short 0 pulse, based on the timing diagram that was given there. So let's see what code I have written. Now I'm going to assume that you know some programming language with C, so we'll cover it fairly quickly, and I will make this code, of course, available to you so you can download and take a look in your own time. So this is the header file. The header file tells us a couple of information. For example, it tells us that we're using a PIC that's an 18F4550, so that grabs all the information for that particular PIC from the compiler, so it knows what instructions set to use and so on. There's a bunch of fuses here. These fuses are compiler dependent. It's telling you, for example, that there is no watchdog timer, or there's no brownout reset, and so on. And it's just some basic things that the compiler will set for you, so don't worry about that so much. This line is interesting and important. It tells us that the crystal oscillator that's used is a 20 megahertz crystal oscillator, as I told you, but the internal clock of the PIC is 48 megahertz. Now, these two numbers, you cannot just have any clock frequency for the crystal, because you have to make sure that the PLL divide ratio inside the PIC supports this ratio between 20 and 48, and that's something you have to look in the data sheet for the PIC. But this particular model, the 18F4550, can create a 48 megahertz internal clock from a 20 megahertz crystal. And then there's a bunch of other information that depends on our setup. For example, I'm telling the compiler that the data input pin that I'm using for the pixel, the NeoPixels, is pin E0. So that's one of the pins of the microcontroller, one of its general purpose IOs. And the number of NeoPixels that I have is 60, and the rest are just some other constants that is used for the code. So really the only interesting thing is that the way I've made the code, the number of LEDs isn't fixed. So if I increase the number of LEDs from 60 to 100, then the code will take care of that and make sure the correct number of bits are sent out. So that's what this section does. So the main code itself is obviously more complicated because I've created a little demo for you guys. So I'll describe only the important parts and then you can go through the rest of it yourself. Now the most critical thing is the portion of the code that generates this waveform. Okay, and oops, I just change the page. There you go. So this is the only thing that matters. So what I've done here is that I've written one function, and that function is called neobit. And what it does is it accepts a bit, either a 0 or a 1, and then based on that it either transmits this waveform or this waveform. Remember, that's all we need to do. The whole programming sequence of these LEDs is just a sequence of sending either this waveform or that waveform. So let's go back to the code. So the code says that if the bit is 1, then set the output to high, then wait for a number of CPU cycles, and then set the output back to low, and then wait some more cycles. But if you note, this portion, this wait cycle is actually commented out. I'm not even using it, and we'll come to that. Now if the bit is not 1, else, which means if the bit is 0, then create a high, then wait for a different number of cycles, and then create a low, and again wait for a different number of cycles. And you can see these are reciprocals of one another. So it waits 6 cycles on the high and then 3 cycles on the low, or it waits 3 cycles on the high or 6 cycles on the low, which essentially is this. So if the bit is a 0, it waits a short amount of time, then a long amount of time. If it's white, it waits a long amount of time and then a short amount of time. So that is taken care of by these two if statements, this if and else statement. But I have put this thing outside of this little 2 brackets, which means that only this part of the code is actually executed. And then if it's a 0, then only this part of the code is executed. So why am I doing that? Well, let's think about it for a second, because you have to appreciate what the CPU is actually doing when it's executing these commands. Now, the function is called, the if statement is executed, and then the CPU will do an output high, then it will wait, then it will do an output low, then it will wait. But once this is over, the CPU now has to come out of the if statement, come out of the function, and then go back again. And that process of coming out of this and coming back and starting again for the next bit actually takes time, because those are instructions in the CPU's instruction set that has to be executed. This is not an atomic command. There is delay that is associated with coming out of this if statement, wrapping around, coming out of the function, coming back into the function, going through the if statement again before you reach the next bit. And that's where the trick is. The fact that the compiler will have to expand this out into a whole bunch of assembly or machine code statements that actually take time, and that you have to take that into account. Going from this command to this command is immediately followed. So from here to here is just right on the next instruction set, but from the next command back onto the beginning is not. There's many other commands that are that have to be taken care of by the CPU, which take time, and we will see that. So what I'm doing right now in the development board, all I've done is that I'm constantly writing the bit 0. That's all. So I have written a code which is not, forget about the rest of this. All my code is doing right now, that is programming into the microcontroller, is constantly setting the bit 0 and nothing else. And I want to make sure that that waveform actually matches this waveform. And which means that the compiler only executes these 3 commands in a row before coming back and doing it again. So it's just going in a loop over and over and over, running this. So what do we expect to see? We would expect to see this waveform over and over again with the timing that is specified here. Well, do we see that or not? So here's my setup. I have not connected the LEDs to anything. All I've done is that I've connected my oscilloscope probe to the pin E0. If you remember, pin E0 is the pin that I'm going to use later for the data input of the NeoPixel LED chain. So I've programmed this microcontroller, as I said, with constantly sending the bit 0 and nothing else. And I have connected the probe to my Tektronix MDO 4104B-6, which you've seen a complete review of before. This is now kind of my default scope that I go to, and I'm looking at the waveform. And the scope, of course, is able to measure for us the exact width of the high and low pulses as they appear. Here we go. So here we go. So you can see this waveform is repetitive. It should be repetitive because I'm constantly sending bit 0 over and over again. So it has a high period and a low period, a high period and a low period. And the high period's width is 400 nanosecond and the low period is 1 microsecond. Now remember, in my code, I didn't even have the delay associated with this part. Even though I have put no delay, this is still longer than it should be. It should be, based on the data sheet, this portion should be 0.4 microsecond, and it is. And this portion should be 0.8 microsecond, but it's already longer than 0.8 microsecond. So even with not putting any delay, I still cannot meet the timing requirement with a C language. But here's the really weird part. It still works. I'm not exactly sure why. I don't know why, even though I'm not meeting the exact timing requirements, I can still program the LEDs fine. I suspect what is important really is only the width of the first width of the cycle and not the second one. If you meet the first width and the second one is roughly close, it will still execute it for you and it will still accept that as either a 1 or a 0. So remember, this is a sequence of a whole bunch of zeros in a row. Now I'm going to change the code and I'm going to send a whole bunch of ones instead. So I'm going to program it again. So have your eye on the waveform. Here we go. Okay, now I'm about to send ones in a row as opposed to zeros in a row. So this waveform should disappear and then it will come back. And then you will see that the order is reversed. Here we go. Now I have long periods of ones and then again a very short period of 0. I cannot meet the 0. Now this 0 should be 0.4 microsecond, but it's not. But I'm meeting the high. The width of the high should be 800 nanosecond or 0.8 microsecond, and it is. It meets that. But the low, again, it doesn't meet that. It's about 3 times longer than it should be. But it still works, and I don't know why. Like I said before, I think it's just because the only thing the IC inside the NeoPixel cares about is to make sure that the width of the high period is correct. And as you saw, between the high and the low, I do have the ratio that is required by the datasheet. I just don't meet the ratio for the low portion of the waveform. Well, it works, and I don't know exactly if you've played around with it and you know why it works despite the fact that it doesn't exactly fit the requirement of the datasheet. Let me know. Well, what is next is let's take a look at the code a little bit more and connect the NeoPixel and see the beautiful blinking lights. So here's the rest of the code. Let's just quickly go over it and see if you can guess what it does. So here's our function that sends our zeros and ones as I described it to you, as we saw, and we saw it on the oscilloscope what the waveform looks like. It still works, and I've left these delays outside because we don't need them. And I have an initialization function, and this initialization function creates an array of colors essentially. So at the very top of the code I have 3 variables. These variables are neo green, neo blue, and neo red. So they are 60 long arrays, which each of them hold the values for the green color, the values for the blue color, and the values for the red color for all the 60 LEDs. And in this initialization function, I give them a particular pattern. So I change the values of green and red and blue arrays in order to give them a particular pattern. All I do is that every 10 LED, I give it a different color. So the first 10 LEDs are only red, then the next 10 LEDs are only blue, and the next 10 LEDs are a combination of blue and red, and so on. So this will create a rainbow ring around the array. And then it will show up and it will light up. But I thought that's too boring. Let's give it some animation. Then I have created something called a Neo Rotate, and all it does is that it rotates the colors between the pixels. So it's going to make it look like as if the colors are rotating in a circle. And all it is doing is it's going through each of the array and assigning the variable of the previous element to the next element. So I'm kind of doing a cyclic shift between the array. Again, very straightforward C code. Go and dig into it and figure it out and play with it yourself. And then there is also a Neo Draw, which then draws out the entire colors by sending it to the NeoPixel by using the NeoBit function. So it just goes through each of the variables in the array, and then one bit at a time it latches them out onto the pin E0, and which then goes into the data input of the NeoPixel ring, and so on and on. So you can figure it out. And then at the end, my main function, all my main function does is that it will initialize the Neo array, then it will permanently draw the array, rotate the array, wait for 25 milliseconds, and then do it over and over again. So you should see a nice ring of colors rotating around. So let me connect it up and show you. So here's our final setup, really straightforward. I haven't done anything. Here's the programmer connected with the ICD to the evaluation board. Now I'm connecting the data input of the NeoPixel to pin E0. I'm grounding the other one, and I'm providing power externally through my Rigol DP116A power supply directly to it. Everything is programmed, the chip is running, and this thing is turned off because the power supply is turned off. So let me go ahead and turn the power supply on, and we should see the ring, rotating ring of colors. Let's see. There it is. Look at that. We'll turn the slide off. Very simple, straightforward. We have a nice rotating. It looks much nicer in person because the camera doesn't have enough dynamic range to be able to capture this. But if I put a piece of paper in front of it, it will diffuse the colors a little bit. If I can hold it on properly, and you can kind of get you can get a really cool, weird effect, really psychedelic things happening here. So there it is. I have made the code. I will make the code available, of course, on the website. You can download it, you can modify it, and if you do make something with these guys, let me know. Post it on as a comment so that we can see. Everybody else can also see. You can very straightforward to program these guys, and you don't need an Arduino. You just need a bunch of C code. And I promise you, if you go through this exercise yourself and program it yourself once, you will develop a very good appreciation for really what's under the hood, and it's a well worth experience. So next, let's talk about the giveaway. Alright, so now it's giveaway time. As you know, the Signal Path is essentially a non-for-profit website. I don't have any advertisements on my own website, and everything that I do is just to give back to the community. It's my way of giving back to everybody who helped me so much when I was learning about these things. I'm always fortunate to have so much equipment, and there's some stuff that I've been sitting around I haven't been using for some time, so I thought, hey, I'll give it back to you guys. My only request is that whoever's asking for these, make sure that you don't have a lot of equipment already. The point is to give away these to people who either can't afford it or don't have access to it. It's difficult for them to get a hold of these. So please be considerate when you're deciding to ask for these. And the way I'm going to choose is that I'll leave comments on the video or on my website, and after some time I'm going to go through all of them, and I'm going to pick one person. Just write 1 or 2 lines saying why you want it or where you're going to use it and what you're going to do with it, so that I can give it to somebody who can put it to best use. So what are we giving away? I'm giving away, first thing I'm giving away is a TPI Scope Plus 440. I've had this thing for a long time. It's a nice little handheld oscilloscope multimeter unit that I used a lot long ago, and it has a whole bunch of functionality. Of course, measures voltage and hertz and logic and capacitors, and it has a little computer serial interface, and it has continuity test, ohms, and so on. It also plots waveforms. I think it has a 20 megahertz or so bandwidth. So it's really nice if you don't have a handheld oscilloscope, if you don't have an oscilloscope at all, and you want to just learn about this. It will be a good starting point, and I will ship this to you. And I'll pay for the shipping myself. You don't have to worry about that. The only thing is that I can only ship within the United States. So I'm sorry all the international viewers, but it has to go in the United States. It's very difficult to ship internationally, test equipment and so on. Anyhow, so if you're in the US and you can use this, let me know. So it comes with the power supply, because it doesn't have an internal battery right now. The battery I took out because it died a long time ago. It would be a good little project to open it up, see what's in it, and put a battery in it. Just remember that it takes nickel metal hydride, and don't put any other type of battery in it. It's going to explode. So, and we have even the instruction manual. I still have this, believe it or not, and of course some probes. And these are all functioning units. You don't have to repair them. I've used them before. So that's the first thing I'm giving away. And I'm not going to give away both of these to the same person, of course, to 2 different people. And the next one is maybe even more exciting. It's a little bit heavier, that's for sure. It's a Tektronix digitizing storage oscilloscope. This is the Tektronix 2232. So it looks like an analog scope, but it's actually a digitizing scope, but it does have that classic analog behavior. It's fully functional, and it has this nice thing here. It is actually fitted with the GPIB option. That's nice because you can get data out of this by storing the waveform and then connecting to the computer and grabbing data out. So the GPIB function is actually a rare addition to this particular model. So this guy is also fully functional. In fact, you've seen this in action in one of my earlier videos. I think it was the ignition coil, that little Tesla coil that I made a long time ago. I used this scope to measure the waveform, so you've seen it in action. You already know it works. And it's a nice little unit, and it even has a lid in front of it, and everything is fully functional again, and it comes with a power cord. And that's it. I'm sorry, it doesn't come with any probes. I don't have any extra probes, but probes are really inexpensive on eBay. Just pick a couple up, for a couple of dollars. It can't be that expensive. And if I find some probes in the meanwhile that I don't need, I have to go through my stuff, I'll include the probe as well, so you can start using it right away. But otherwise, it's a fully functioning unit. So what do you have to do? Go on YouTube, leave a comment, as I've said, on the video, and also on my website. These are the only two places I'm going to look, on my website or on YouTube, because it's the easiest places for me to check. And let me hear from you, and of course you can discuss the video that that I showed you about the NeoPixels, and I'll make the code available. And I'm looking forward to hearing from all of you again, and thanks as always for the kind comments. It's nice to hear that so many people are enjoying the videos, and I enjoy making them. So until next time.